You have seen a lighthouse before, or you know what one looks like. A tower on a cliff or a pier, rotating beams sweeping through darkness, marking time with light, on and off, regular as a heartbeat. Sailors use it to navigate, to find home, to know where they are when everything else is dark. The universe has lighthouses too. They are not built by anyone. They are not constructed or maintained or guided by human hands. They are dead stars, and they are blinking at you across billions of miles of empty space. Right now, in this moment, they are sweeping their beams through the darkness, and we can see them. We can detect them. We can even hear them if we translate their light into sound. One of these lighthouses blinks 716 times per second. That is not a metaphor. That is not poetic exaggeration. A dead star, the remnant of something that once was alive with nuclear fusion, is rotating so fast that it completes 716 full revolutions every single second. It is a lighthouse that turns almost 2,000 times faster than a ceiling fan on high. Its beam cuts through space in regular pulses, and we see it flash on and off and on and off, hundreds of times each second. It is called a pulsar, and the first one was discovered by accident. In 1967, a graduate student named Jocelyn Bell Burnell was looking at radio telescope data. She was studying quasars, distant objects that nobody really understood. But in the data, she found something else. A signal, a pulse, a regular, repeating beat coming from somewhere in the sky. The pulse was so regular, so impossibly precise, that at first she thought it must be an error, or interference from Earth, or a transmission from an alien civilization. She called it LGM-1. It stood for Little Green Men, because that was the only explanation that made sense. No natural object could produce something this regular. Nothing in the universe worked like a clock. But it was not aliens. It was something far stranger. What Jocelyn Bell Burnell had discovered was the lighthouse beam of a dead star. She had detected radio waves coming from a neutron star, the crushed remnant of a massive star that had exploded. And because the neutron star was rotating, its beam pointed at Earth once per rotation, like a lighthouse sweeping past a ship. Every time the beam pointed toward us, we detected a pulse. Every time the beam rotated away, we saw nothing. On and off, on and off. Perfectly regular, perfectly predictable. The universe was not communicating. It was not sending messages. It was just dying. And in its death, it had become precise. When she announced the discovery, it changed astronomy forever. We had found a new kind of object, a new kind of dead star, a lighthouse in the void. And once we knew what to look for, we found thousands of them. Thousands of these blinking remnants, sweeping their beams through space, marking time with the regularity of atomic clocks. Pulsars are the heartbeat of dead stars, and they are still beating. But to understand what a pulsar is, you have to understand what had to die to make it. You have to understand what happens when the biggest, brightest stars in the universe run out of fuel. You have to understand what it means when billions of tons of matter gets crushed into a space so small that it should not exist. You have to understand how something can be dead and still keep beating. Let us start with a star that is still alive. Our sun. It is 93 million miles away. That is close enough that we have evolved to see it. Close enough that it feels warm on your skin. Close enough that it does not feel incomprehensibly distant. You can look up and see it. You can see it rise and set. It feels manageable. The sun is about 865,000 miles wide. If you wanted to walk around its equator, you would walk 2.7 million miles. That is far. But you can comprehend it. It is a number. You can hold it in your mind. Now imagine a star 20 times bigger than the sun. That is not unusual. There are many stars much larger than our sun. The star Betelgeuse is about 700 times wider than the Sun. If you replace the Sun with Betelgeuse, the outer edge of it would be somewhere beyond Jupiter's orbit. The entire solar system would be inside this one star. Betelgeuse is a red supergiant. It is old. It is close to the end of its life. It has fused hydrogen into helium. Then it has fused that helium into heavier elements: carbon, oxygen, silicon, iron. It has been building heavier and heavier elements in its core, layer by layer, like the rings of an onion. But it cannot fuse iron. Iron is the end of the line. Once a star starts making iron, it is dying. It cannot get any energy from fusing iron. The star is still burning. It is still hot, but it is already dead. It just does not know it yet. For a while, nothing happens. The star keeps existing, keeps shining, keeps sweeping its light across space. But the iron accumulates. It piles up in the core. The pressure and temperature keep rising because the star keeps contracting under its own weight, trying to fuse something that cannot be fused. Then, suddenly, the pressure becomes too much. The core collapses. Not slowly, instantaneously. The iron cannot support the weight above it. The core implodes. All of that weight, billions of tons of stellar material, falls inward in a fraction of a second. The density becomes incomprehensible. Electrons are forced into protons, forming neutrons. The iron nuclei touch each other. They merge. The core gets denser and denser and denser until something pushes back. For a moment, something does. The neutrons push back. They cannot be compressed any further. At that point, the infalling material rebounds. It bounces off the incompressible core, and it bounces hard. The rebound creates a shock wave. Energy. Heat. The outer layers of the star are suddenly heated to billions of degrees, and they explode outward. This is a supernova, one of the most violent events in the universe. A single supernova can outshine an entire galaxy of billions of stars. For a few seconds, one dying star becomes brighter than billions of stars that are still alive. The explosion tears the outer layers of the star into space at speeds of 20,000 miles per second. That is 10% the speed of light. The explosion releases as much energy in a few seconds as the sun will release in its entire lifetime. But it leaves something behind. At the center of that explosion, the core remains, incompressible, crushed. What was once a star the size of Betelgeuse is now a sphere about 12 miles wide. All of the mass, all of the weight, all of that stellar material crushed into a space smaller than a city. This is a neutron star. Try to picture the density. Take the sun, crush it, compress every atom, every electron, every bit of matter, until it is all forced together into neutrons that touch each other with no space between. Compress the entire sun into a ball the size of Earth. That would be a neutron star. Now do the same thing again. Take that sun-sized ball and compress it further. Make it the size of a city. Make it 12 miles wide. Do that to our entire sun. The sun's mass is 2 times 10 to the 30th power kilograms. That much mass, compressed into a sphere 12 miles wide. One single teaspoon of neutron star material would weigh as much as Mount Everest. A piece the size of a marble would weigh as much as the Great Pyramid of Giza. A piece the size of a grain of sand would weigh millions of tons. But there is something stranger than the density. When a star explodes as a supernova, it does not just die quietly. It does not stop rotating. A star that was rotating once every 30 days keeps its angular momentum. All of that spin, all of that rotational energy, gets transferred to the tiny core that remains. It is like taking all the spin from a massive wheel and suddenly concentrating it into a tiny marble. The marble spins. The neutron star that remains from a supernova is rotating rapidly. Some rotate once every few seconds. Some rotate several times per second. The fastest ones we know of rotate over 700 times per second. Imagine a sphere 12 miles wide. Imagine it is made of the densest material that exists. Imagine it is rotating 700 times every second. The surface of that star is moving at 10% the speed of light. It is moving so fast that the centrifugal force nearly tears it apart. The only reason it does not tear apart is because the gravity is so strong that it crushes everything inward. And as this neutron star rotates, its magnetic field rotates with it. The magnetic field is incredibly strong, trillions of times stronger than Earth's magnetic field. As the field rotates, it accelerates charged particles. The particles are funneled down toward the magnetic poles. At the poles, the particles are accelerated to nearly the speed of light. They shoot out as beams. Two beams of radiation, like a lighthouse beam, pointing out from the north and south magnetic poles. If the Earth happens to be in the path of one of these beams, we see a pulse. The beam points at us. We detect radiation. Then the star rotates, the beam points away, and we see nothing. Then it rotates back. The beam points at us again. Pulse. Darkness. Pulse. Darkness. Over and over. Hundreds of times per second. Jocelyn Bell Burnell discovered the first pulsar in 1967. It was rotating about once per second. Since then, we have discovered thousands of them. We have mapped them. We have cataloged them. We have found pulsars in nebulas and clusters and scattered throughout the galaxy. And here is the part that gets you. They are incredibly far away. The closest pulsar to Earth is about 280 light-years distant. Light from that pulsar takes 280 years to reach us. That means we are looking at light that left that star when Thomas Jefferson was president. We are detecting photons that have been traveling through the darkness for nearly 3 centuries. And it is the closest one. There are pulsars thousands of light-years away. 10,000 light-years. The light from those pulsars left when human civilizations were just beginning to record history. The pulsars themselves may not even exist anymore. They may have cooled down. They may have been swallowed by black holes. But their light is still coming, still pulsing, still beating the rhythm of a dead star's rotation. We can detect these pulsars with radio telescopes. We can measure their pulses. We can predict exactly when the next pulse will arrive, down to the microsecond. Pulsars are so regular, so precise, that they rival atomic clocks in their accuracy. Scientists have used pulsars to measure the expansion of the universe. We have used them to test the theory of relativity. We have used them to navigate spacecraft billions of miles from home. A dead star, crushed to the size of a city, rotating hundreds of times per second, its beam sweeping across billions of miles of space, has become our clock, our compass, our lighthouse in the void. But there is something else. Something that should make you stop and really think about what you are looking at. The pulses from these distant objects are not coming from something that is moving toward us. They are not coming from something that is moving with us. They are coming from objects so distant that their light takes centuries to reach us. The pulsars are in fixed locations in space. They are static, unchanging, except for the rotation that creates their pulse. And that means the pulsars we are detecting now have been beating their rhythms in darkness for thousands of years, billions of years, for some of them. Rotating, pulsing, sending out their beams into the emptiness. Completely alone. No witnesses, no observers, just a dead star, doing what it does forever and ever, until it finally cools down and goes dark. We are the first thing in billions of years to notice. There is something profound happening when you detect a pulsar. You are looking at the remnant of a star that died before your species existed. You are detecting light that traveled longer than human civilization has been recording time. And you are using that light to measure something about the universe itself. You are using a dead star as a tool. Jocelyn Bell Burnell did not know that when she discovered the first pulsar, she was discovering something that would help us understand gravity. She did not know that pulsars would become some of the most valuable tools in astronomy. She thought she had found aliens. Instead, she had found a beacon, a lighthouse built by the universe itself. Pulsars are not alive. They are not thinking. They are not aware of the light they are sending out or the fact that something billions of miles away is detecting it. They are just the remnants of stellar death. But they are performing a function. They are marking time. They are sweeping their beams through the darkness with such regularity and precision that we can use them to navigate. The universe, in its death, has become useful. This is not poetic. This is not exaggeration. Right now, NASA engineers are using pulsar data to help spacecraft find their way through the solar system. Pulsars have a precision that matches atomic clocks. If a spacecraft knows where the pulsars are and can detect their pulses, it can calculate its own position without needing to communicate with Earth. A dead star, billions of miles away, becomes a GPS satellite, a lighthouse for ships in the cosmic ocean. Every pulse you detect is a click, a tick, a heartbeat. And that heartbeat has been going on for thousands of years, billions of years for some pulsars. Just a dead star, doing what it was built by physics to do, rotating, sending out its beam, marking time with perfect regularity. And then one day, a human being pointed a radio telescope at the sky and heard it. The pulsar did not change when we detected it. It is not aware that we are listening. It will keep rotating and pulsing long after we are gone. But for this moment, for this brief intersection in time, we are connected to it. We are using it. We are learning from it. This is what it means to be conscious in a universe that contains dead stars. It means that the remnants of stellar death can speak to us if we know how to listen. It means that the universe has left us clues, beacons, lighthouses in the void that existed long before we learned to see them. The stars in the sky are not constant. They are not eternal. They are born. They live. They die. And in their death, some of them become something else. Something that marks time. Something that sends out a signal across the darkness. A pulsar is a dead star that still has something to say. It is saying, I was here. I lived. I burned bright. I exploded. And now I am still here, still rotating, still sending out my beam into the darkness. And if you are clever enough to listen, you can hear me. You can measure me. You can use me to understand the universe better. This is the heartbeat of a dead star. This is the sound of something that should be gone but refuses to be forgotten. This is the universe's way of leaving a message across billions of years and billions of miles. We are lucky enough to be here at the moment when we finally learn to hear it. The pulsars will keep beating long after we are gone. The lighthouses will keep sweeping their beams through the empty darkness. New ones will be born from supernova explosions. Old ones will eventually cool and fade. But for now, in this moment in time, they are still here, still pulsing, still alive with the physics of a dead star's rotation. The universe sent out lighthouses across the darkness, and we finally looked up and saw them blinking. Pulse, darkness, pulse, darkness, pulse. The heartbeat goes on.